our school. And we are happy to have the third lecture by Kazuo YONEKURA.
Okay, thank you very much. So yesterday, I discussed some examples of global anomalies in the case of one-dimensional fermions, but the method which I used yesterday was not so systematic. So today and tomorrow, I'd like to discuss more systematic description of anomalies, and in particular fermion anomalies. And they are now known to be described by what is called Atiyah-Padsinger Yeta invariant. So that Yeta invariant is the general formula for anomalies of fermions. And that Yeta invariant also contains the information of perturbative anomaly and also non-perturbative anomaly. And it is believed that that Yeta invariant is the complete description of anomalies of fermions. So I want to explain the physics argument to derive this general formula. So first, for that description of systematic description of anomalies, first I'd like to construct chiral fermions as edge modes or boundary modes of higher dimensional theory. So first let me explain the setup. So we want to study anomalies of theories in D dimensions. So I consider some D manifold. So this W is a D-dimensional manifold. And I also introduce some D+1 dimensional manifold. And I will later consider massive fermions on this D+1 dimensional manifold. And then I realize massless chiral fermions on this D-dimensional space. Sorry, so I have to say that this Y is a manifold with boundary, and the boundary is W. So this is the relation between this Y and W. And whenever I say manifolds, I also assume that I put the background fields of symmetries. For example, if we have U1 symmetry, then I assume that I put U1 gauge field here and also here. So it is always implicitly assumed that I put some background fields for the symmetries. Okay, so the situation is something like this. So we have a boundary manifold, which is this W, and this bulk is Y. And also, for later convenience, I take a coordinate which is orthogonal to this boundary. So yes. So I take this coordinate which I call tau. So this is a coordinate which is orthogonal to this boundary, and I assume that this boundary is located at tau equals 0. And this coordinate is defined only near the boundary. So this coordinate is not very defined inside of this bulk, but it is very defined near the boundary as a distance from this boundary. And I also assume for technical simplicity that near the boundary, so I assume that there exists some number epsilon such that the region near the boundary is just a product form. So near the boundary, so the manifold is just a product, and I also assume that the gauge fields in this region is just a pullback from this boundary. So that means that the gauge fields does not depend on this coordinate tau near this boundary. Maybe I should write it more explicitly. So gauge fields, so does not depend on this tau, and also the tau component of the gauge field is 0 in this region, in this neighborhood of the boundary. So this is the basic geometric setup. And in this setup, I consider massive fermion in the bulk T+1 dimension and its Lagrangian is simply just the standard Dirac Lagrangian. So this is a very familiar Lagrangian of fermions. And here, just for simplicity of presentation, I treat the case of Dirac fermion, but it is also possible to describe Majorana fermions. In the case of Majorana fermion, we just need to take this psi bar to be roughly psi up to some matrix. Then we can also discuss Majorana fermions. But just for simplicity, I discuss the case of Dirac fermion. And so because we consider fermions, we have gamma matrices. And in particular, there is a gamma matrix in the tau direction, which I denote by gamma tau. So this is gamma matrix in the direction tau. And gamma matrices, of course, satisfy the standard algebra. I mean, in the orthonormal system of coordinates, it's like this. So in particular, the square of this gamma tau is just equal to 1. So this means that this gamma tau has eigenvalues plus or minus 1. So I take this gamma tau and then I impose some boundary conditions by using this gamma tau. So because we are considering manifold with boundary, we have to put some boundary condition on the boundary. And I choose the following boundary condition. So I impose the boundary condition, which I call L, that 1 minus gamma tau acting on psi at the boundary tau equals 0. This is 0. So this means that at the boundary, I require that the Fermi field is an eigenvector of this matrix gamma tau with eigenvalue plus 1. So that is the meaning of this boundary condition. So the components of this Fermi field with eigenvalue minus 1 is set to be 0 at the boundary. So so we can impose this boundary condition, and one good thing about this boundary condition is that we can impose this boundary condition no matter what symmetry we consider. So this boundary condition always exists, and this is consistent with any symmetry. Yeah, for example, if we have some U1 symmetry or SUN symmetry or some symmetries, this boundary condition is obviously consistent with these internal symmetries. And maybe it is not so easy to see, but it's also consistent with some more subtle symmetries, such as time reversal symmetries. So anyway, we can impose this boundary condition, and I impose this one. Then I want. Oh.
I have a question.
Yes.
So I was wondering, so far you need not have taken D to be even or odd, right? So far the bulk and the boundary could be any dimensional.
Any dimension, yes, exactly. Yeah, and also, yeah, that is important because so perturbative anomalies exist only in even dimensions.
Yeah.
But global anomalies exist in any dimensions. So yeah, it's important to treat the general dimension. Thank you.
Thank you.
Okay, now I want to study the behavior of this theory near the boundary. So near the boundary, so I want to study the Dirac equation. So Dirac equation is, so this quantity is 0. So this is the Dirac equation of motion. And this can be rewritten like this. So we take gamma tau, and then we can write it in this way. Yes, in this way. And here, this dw is defined as follows. So this dw is basically this is a Dirac operator. Dirac operator on the manifold W. So we can write this Dirac equation like this using the derivative in the tau direction and the Dirac operator in the W direction, and also this mass term. And I study the behavior of this fermion near the boundary in the large mass limit. So I take this M to be very large. Then it turns out that there is a localized mode near the boundary. So there is a solution of the Dirac equation, this bulk Dirac equation, which is localized near the boundary. But for this solution to exist, this mass parameter must be negative. So let me write down this localized solution. So it's given as follows. So this Fermi field psi is taken to be a product of some field chi times exponential minus m tau. And this chi only depends on the coordinates of W. So the tau dependence is only here. And so this chi depends only on the coordinates of W, the boundary. And also chi is assumed to be the eigenvalue of gamma tau with eigenvalue 1. So this is 0. And also this chi is assumed to satisfy this equation. So this is basically the Dirac equation on the boundary. Then we can easily check that this is a solution of the Dirac equation. So first of all, it satisfies the boundary condition trivially because so the boundary condition is that this quantity vanishes on the boundary, but this is equal to minus gamma tau chi. Yes. And I imposed this condition on this chi, so this is 0. So it satisfies the boundary condition. And also this solution satisfies the Dirac equation. So the Dirac equation, the bulk Dirac equation was given by this one. So if this vanishes, then that means that this satisfies the Dirac equation. So let's check this. So this is, so from the derivative of this derivative with respect to tau, we get minus m. And from this Dirac operator on W, we just get 0 because I assumed that this chi is annihilated by this Dirac operator. So this is 0. So this term is 0. 0. And finally, this last term, this gamma tau is just plus 1 because I took this chi to be an eigenvector with eigenvalue plus 1 under this gamma tau. So we have m. So this is 0. So this ansatz satisfies Bonn's boundary condition and the Dirac equation. So this is really a solution. And so this is so localized near the boundary if the mass parameter is negative. So by my convention, this tau, the bulk is in the region of negative tau. So that was my convention. Let's go back to this figure. So tau was a coordinate which was orthogonal to this boundary, and this bulk region is in the region of negative tau. So that was my convention. And then, so this tau is negative, and also this m mass term is negative. So this exponential of minus m tau behaves like this. So this is exponentially localized near the boundary. And this localization becomes better and better if this mass parameter, the absolute value of this mass parameter becomes bigger and bigger. So in the infinite mass limit, this mode is completely localized on the boundary. But this solution exists only if the mass parameter is negative. So, so that is also important. So this exponential minus m tau. So this is localized near the boundary if and only if this m is negative, and there is no such localized mode. Sorry. For positive mass parameter. And in the context of condensed matter physics, this parameter region, positive mass parameter, is called trivial topological phase, and this region, negative mass, is called kind of non-trivial topological phase, and I will discuss a little more details later. But anyway, so here the important point is that the behavior of the theory is different depending on the sign of the mass parameter. So there are two different phases. Okay, so we get localized mode on the boundary. And this gamma tau can be regarded as a kind of generalized chirality operator. On the boundary. So in particular, this gamma tau anti-commutes with the Dirac operator on W. So this is one of the basic properties which must be satisfied by a chirality operator. And if we regard this gamma tau as a chirality operator, then this chi is a massless chiral fermion. On the boundary. So this chi is a chiral fermion because it's an eigenvector with eigenvalue +1 under this gamma tau. And this is a massless fermion because it satisfies massless Dirac equations on the boundary. So in this way, starting from a D+1 dimensional massive theory, we can get a chiral fermion on the boundary. For example, so if we consider D+1 equal 5, so if we consider 5-dimensional bulk, then we have 5 gamma matrices, gamma 1, gamma 2, gamma 3, gamma 4, gamma 5. Then we can take this gamma tau to be just gamma 5. So this is a well-known chirality operator in 4 dimensions. So this is the most famous case. So I believe that this gamma 5 appears in any textbooks of quantum field theory. So by this construction, we can obtain chiral fermions of 4-dimensional chiral fermions from the 5-dimensional bulk massive fermion. And this, in that case, this gamma tau is really this gamma 5. It's a very famous chirality operator in 4 dimensions. But in any dimensions, we can just regard this gamma tau as a chirality operator in some generalized sense. Okay, and also we need to regularize this theory, and it is convenient to use Pauli-Villars regularization for this system. So I mean, I'm just considering free massive fermions. This fermion is free because I'm just taking gauge fields as a background field. So I'm not integrating over gauge fields. So in that case, the most convenient regularization of fermions is Pauli-Villars regularization. And I take Pauli-Villars mass to be positive because I don't want any localized zero modes from Pauli-Villars regulators. So if I take Pauli-Villars mass to be positive, then there is no localized mode. From unphysical Pauli-Villars field. So this condition is necessary for physically sensible theory. So if we get some massless fields from Pauli-Villars fields, then that violates some physical principles such as unitarity. So I need to take this mass parameter to be positive. Okay, so here I mentioned some four-dimensional example, but let me also give another example to demonstrate that this construction is very general. So by this construction, so if I take this t plus 1 to be 2, and if we consider Majorana fermion, then I can obtain one-dimensional fermions, which I discussed yesterday. So I take Majorana fermions with ON symmetry. So under ON symmetry, so these fermions are rotated like this. So this is the same symmetry which I discussed yesterday. And in the bulk 2 dimensions, I take the action of the massive Majorana fermion to be like this. Trace of psi I. So the details are not so important, but let me just write the equation for completeness. And here this epsilon is an antisymmetric matrix. And gamma tau is matrix like this, and gamma sigma is like this. So I don't show it explicitly here, but you can show that this Lagrangian is Lorentz invariant, and because of this antisymmetric matrix here. So let's just take this action, and then in this massive fermion theory, there is a localized mode. So which is so including coefficients, the localized mode is given by this formula. So maybe I should define tau and sigma. So we have 2-dimensional space-time, which is Euclidean space-time, and so what I call the W is, maybe I changed color. So what I call the W is here, and what I called Y is this half plane. Then I obtain this kind of localized mode. And by very simple calculation, by just substituting this expression into this action, it's an easy exercise. So if you have time, then please do it by yourself. Then after easy computation, we get the following action. So this is exactly the action of the one-dimensional massless fermions, which I discussed yesterday. So in this way, we can realize this theory as a boundary mode of a bulk massive fermion. And it turns out that this construction is really very general. So we can construct any fermions from a higher dimensional D+1 dimensional massive fermion. Okay, so this concludes the construction of boundary chiral fermion. Then I can now go to the discussion of anomalies of these chiral fermions. So we considered the manifold Y with boundary W, and I imposed the boundary condition, which I denoted by L. Then we can consider the partition function of the theory on the manifold Y with boundary condition L. So I denote this partition function as z of y comma L. So this is given by the path integral of the massive fermion in the bulk.
Sorry, I have a question.
Yes.
So before we go on, so I didn't really understand why we were doing this Pauli-Villars regularization before. So why do we need to do this Pauli-Villars regularization? What do we need to normalize?
Okay, so I will later explicitly use this Pauli-Villars regularization. So maybe.
Okay, you will use it now. Okay,
yeah,
okay.
Yeah.
Okay, and also another question regarding that. So you said you had to take the mass of the Pauli-Villars field to be positive, so there is no localized mode.
Yes.
But I guess you could also just take a scalar particle, no, to do Pauli-Villars regularization, and then there will be no localized mode, right?
Scalar field. No, I mean, so I think there is localized mode if the mass is negative. So the Pauli-Villars field has the same action as this one.
Okay.
So I mean, so only the statistics is different, but to show the existence of the localized mode, I just used the Dirac equation, and that Dirac equation also applies to Pauli-Villars field. Okay. So I need to take the Pauli-Villars mass to be really positive.
Okay. Yes. If it follows Dirac equation, yes. Thank you.
Okay, so I consider this partition function And for negative mass parameter, the bulk is gapped. So it has a large mass gap. Given by the absolute value of m. And I take this absolute value of m to be infinity. So this means that the mass of the bulk field is infinity. So in the low energy limit, there is no degrees of freedom in the bulk. But on the edge or boundary, maybe I should write boundary. We have a chiral fermion. Is chi. So the only low energy degrees of freedom of the system is this chiral fermion. So there's no degrees of freedom in the bulk, and we only have this chi on the boundary. So physically, we expect that the partition function of the bulk theory, this partition function, is essentially equal to the partition function of this boundary chiral fermion. So we want to think that this partition function with boundary condition L is actually the partition function of this chiral fermion on d-dimensional manifold. So if we can really identify this partition function as a partition function of the chiral fermion, then this equation gives a definition of the partition function of the chiral fermion. So I want to take this this bulk partition function as a definition of this chiral fermion partition function. But there is a problem. So this left-hand side this has a very good property. This is completely gauge invariant. However, this left-hand side may depend on y. So we want to define the partition function of chiral fermion on a d-dimensional manifold in a gauge invariant way. And gauge invariance is guaranteed by this construction. Because so this left-hand side is gauge invariant. I mean, so that is true if we use Pauli-Villars regularization, and I will later more explicitly use Pauli-Villars regularization, but Pauli-Villars regularization guarantees that we can regularize this expression in a gauge invariant way. So this is nice. We get a gauge invariant definition of the chiral fermion partition function. But now the problem is that this definition depends on how to take this bulk, even though we are interested in d dimensions. So this is a modern understanding of anomalies. So this is an important point. So let me write it. So modern formulation of anomalies is the following. So,
Because we have a question in the chat.
yes, chat, okay. What gauge symmetry? Okay, so I didn't explicitly specify the symmetries, but for example, I mean, so the fermions I'm talking about can have any kind of symmetry. So for example, in this example, these Majorana fermions with this action have this ON symmetry. And we can consider any such symmetries. So I discussed it in very general but abstract way. So I didn't mention the symmetries explicitly, but so this psi can have any symmetry, maybe U1 symmetry or SUN symmetry or whatever symmetry you like. And then I introduce background fields for that symmetry. So implicitly, the background field is here. So it is a Dirac operator, and it is given by the covariant derivative, and this covariant derivative contains gauge field. So we have gauge field for the symmetries, and the gauge invariance means gauge invariance under the gauge transformation of this gauge field. So is it clear? Okay. Okay, so the modern formulation of anomalies are the following. So first, everything is formulated in a completely gauge invariant way. So this is quite different from the old treatment of anomalies. So in textbooks, anomalies are described as a violation of gauge symmetries. But here, I'm formulating everything in a gauge invariant way. So it's really important. So there's no violation of gauge symmetry at all. But the definition of the partition function or definition of the D-dimensional theory may depend on the D plus one dimensional bulk. And this definition, this dependence of the theory on the D plus one dimension is the anomaly in the modern understanding. So tomorrow I will talk more details about what kind of dependence I'm talking about. So I'm just abstractly saying that this D-dimensional theory depends on D plus one dimensional theory, but we can really isolate the dependence on D plus one dimensional theory. And so this dependence on D plus one dimensions is described by the Atiyah-Patidzi-Singer data invariant. And tomorrow I will discuss that point. Okay, so maybe I should finish today. Okay, thank you very much.
Okay, so let's thank Kazuya for the lecture. And now we can stop recording and proceed to the discussion session.
Yes, the question is whether you had only, imagine that you had, for example, a charge n particle and not the previous ones. Or charge 3, so you can only construct multiples of 3. So that's what we mean with complete, that you need to have the charge 1.
But how do I know if I have charge 3 or 1? Because I can always redefine the coupling constant. So suppose I start.
Yeah, sorry. So this is why it depends. Like you need information about the full theory in the sense that you need information also about the monopoles.
Okay.
So when we talk about completeness of the spectrum, it's going to be completeness of the electric and the magnetic spectrum. Like you also need the monopoles to break the magnetic symmetries. And since you need both, then by Dirac quantization, right?
Yes.
You can define what is the charge 1 in terms of the other one.
So, but then do you need to discuss these higher form symmetries? So can you just assume that there's monopoles and you have to do Dirac quantization then?
Yeah, like you need, it's not assumed that you also need the monopoles to break the magnetic symmetries, because otherwise maybe you can get rid of the electric ones, but you still have some magnetic one for symmetry.
Okay.
And then like you need both to get rid of all the symmetries, and then precisely thanks to the fact that you have both, like you can define what is your lattice, right? So the typical way to proceed is just like, I mean, originally you can have some gauge theory and you can define what is the lattice of gauge charges that is consistent with Dirac quantization. And I mean, if you have just a U1, it's easy because you just have the integers, no, for both electric and magnetic. More generally for other gauge groups and disconnected gauge groups, I mean, you can have many different types of representations, which are not so trivial. But in general, given some gauge theory, you can define what is the lattice that you have. And then the full lattice have to be complete. All the representations, including the monopoles, including the magnetic ones.
Okay. So you need to introduce monopoles to respect this no global symmetry.
Yes.
Okay, interesting.
Okay, it's clear. Any other question?
Thank you. Yes.
Okay, so we have spent 2 days talking about global symmetries because it's well, you will see that many of the other things just come from refining these statements of how much we can break this symmetry. So it's a very central topic. Although as we discussed, sometimes it's not so useful for phenomenology, right? Because I mean, we are just saying that we cannot have an exact symmetry, but as long as we break it a little bit, it seems that everything is fine again. So what we want to do now is to make this more precise and quantify how close we can get to the situation of restoring a global symmetry. Because this, if we are able to do this, this can have much more important implications for phenomenology. So the weak gravity conjecture and the distance conjecture, I don't know, maybe you have heard of, and that are formulated by different means, actually now we can have an understanding of them also as quantum gravity obstructions to restore some global symmetry. So I'm gonna explain it this way, okay? I'm gonna start asking like how close we can get to restore a global symmetry, study what is the physics that appears there, and then connect how this connects with the weak gravity and the distance conjecture. So yesterday I started saying that restoring a global symmetry is going to be equivalent to moving in a modular space, okay? So in string theory, all the parameters, the continuous parameters are parameterized by vacuum expectation values of the scalar fields, okay? So everything is dynamical. And then we have some moduli space, which is the fielded space, no? That's the different values that these scalar fields can take. And we can move in this moduli space and get different effective field theories depending what point of this field space we are, because this will imply that we have different values for the parameters, no? For the coupling, the masses, and so on. So you could then wonder, okay, if I can move in this field space, what happens if I move in such a way that, for example, a gauge coupling goes to 0? Okay, so let me put a bit more bright. They don't see. Okay. Yeah, so I have some gauge coupling that goes to 0, and this is going to be equivalent, yeah, as I said, to moving, I mean, taking this limit, like moving some limit in this modular space. And then in the moment in which the gauge coupling becomes 0, this is going to restore a global symmetry, right? Because we turn off the dynamics of the gauge field. It's like engaging the symmetry. And we restore, for example, if we had some U1 gauge theory, then we restore some U1 global symmetry, 0 form global symmetry. Okay, now you would say, okay, but something has to be wrong now, because we have said that global symmetries are not allowed in quantum gravity. So how string theory deals with this? Well, the point is that these points, as I mentioned yesterday, are pushed away to the boundaries of the modular space. Okay, so they happen to be at infinite distance. Okay, otherwise, if they would be at finite distance, it would be like restore a global symmetry in the middle, and that would give rise, that would be a contradiction with not having global symmetries. So the point is that what happens is not that that point is not allowed, like it's far away, it's infinitely far away, but that as we are approaching the point, we are getting a better, a more approximate global symmetry and closer to be exact. And this is I'm gonna give you what is the conclusion of what happens when you study this in string theory. But what happens is that the effective field theory is breaking down in a continuous way. Okay, it's not only that that point doesn't make sense, it's also that as you approach the point, the cutoff of the EFT goes to 0. Okay, so that there is always some energy regime in which the effective field theory makes sense, but this is smaller and smaller. Okay, so when you try to engineer a global symmetry, the range of energies that you can describe gets shrink, gets smaller and smaller. And this is purely a quantum gravitational effect, because in quantum field theory, it's not only that global symmetries are fine, but also that these limits in which you have some large field range, or more intuitively, when you have a very small gauge coupling, are completely fine, right? Like small gauge coupling is something that we like in quantum field theory because we have a perturbative gauge theory, and there is nothing wrong with that. Like it's precisely the limits in which we have computational control in quantum field theory. So quantum gravity, this idea of no global symmetry is telling us that there are quantum gravitational effects that imply that precisely in these limits in which we have in principle computational control, something has to go wrong. The effective field theory has to break down. There is new physics that must appear. So the EFT, let me write it so it's clear, breaks down when approaching these points, because there is an infinite tower. This is what we observe. There is an infinite tower of states that become light and massless at that point. Okay. So since we are considering effective field theories that are weakly coupled to Einstein gravity, having an infinite tower of states necessarily implies the breakdown of the EFT, and it's a drastic breakdown. It's not just that you can just integrate in a few states and you have a new quantum field theory description. Like we cannot have infinite fields weakly coupled to Einstein gravity. Like the scale at which quantum gravitational effects become important goes to 0. Okay, so something drastic has to happen. Maybe you get a string perturbative limit and you get string theory, or you grow extra dimensions and we'll see different possibilities. Okay, but it's a drastic thing coming from quantum gravity. And yes, I see there is a question.
Are these states always charged?
Okay, so if there is a gauge coupling, if there is a gauge coupling that goes to 0, yeah, there is a tower of states that is charged, and we'll see that in all the examples, and what will be the conjecture is the weak gravity conjecture, so that the mass is smaller than the charge. If there is no gauge coupling, you could wonder more generally what happens when we approach a boundary of the modular space, because maybe we restore a global symmetry, which is not necessarily associated to a gauge coupling. And then you would say, okay, then it's not necessary that the tower is charged in that case, if there is no gauge coupling. But we don't have any example of that. Like all the examples we have in string theory so far, I don't know why, have always a p-form gauge coupling that goes to 0 asymptotically. So there is always a charged tower. We don't know if that's a matter of the lamppost, but yeah, that's what happened so far. But in principle, what the distance conjecture would require is just that there is an infinite tower. I mean, doesn't impose that it's charged. Okay, so
sorry.
Yes.
If we decouple this effective field theory from gravity, we need to recover the description of the standard model, for example, in some scale, right?
Well, the standard model is coupled to gravity, no? I mean, you can, it's not.
Yeah, but only an example, a standard model, but you recover an effective description of a system. If
we send the Planck mass to infinity. So okay, let me say what happens is that the mass of this tower over the Planck mass is always in Planck units, goes to 0. Okay, so this is very important. All the Swampland constraints are always in terms of the Planck mass, such that precisely when you send the Planck mass to infinity, I mean, this becomes trivial. And it could be that the mass of the tower is still infinite, is very heavy. It's just that this massless in comparison to the Planck mass, but if the Planck mass goes to infinity, this has no effect.
Yeah, the problem arises when we couple effective field theory with gravity, right?
Yes.
Okay. Thank you.
Yeah, this only happens, it's a quantum gravitational effect. So only happens when the EFT is quickly coupled to gravity. And therefore the mass of the tower goes to 0 only in terms of the Planck scale. So it's only massless when the Planck scale is finite. Okay. So yeah, this is what happens. Okay, so we have this tower of states, which implies that the cutoff of the theory goes to 0. And this is how it goes to 0 in all the examples of string theory we have, and also what goes to 0 according, this is what will give rise to the weak gravity conjecture, and this to the distance conjecture. Okay, so that in terms of the field distance, that do you travel in the field space, it goes exponentially to 0. And in terms of the gauge coupling, if there is a gauge coupling, it goes linearly, okay, to 0 in terms of the gauge coupling. So when the gauge coupling goes to 0, the cutoff goes to 0. Any other question?
Irene, I have a question.
Yes.
So as you said, in string theory, there are no parameters because all parameters really are expectation values of some field. So this has some flavor similar to the fact that symmetries has to be gauged, they cannot be global, but it's not quite the same thing. So is there a gravity conjecture that says that this should be also the case in quantum gravity, or
that all the parameters are parameterized by scalar fields?
Yeah, that there are no, that in quantum gravity there are no parameters.
Yeah. There is a symmetry associated to it, which is a -1 for global symmetry. So yeah, like a -1 for global symmetry, the current is a parameter.
Okay.
Okay, so the current is always like you have to sum +1, right? So the -1 for global symmetry, you have a current which is a parameter. And then you can wonder whether this -1 for global symmetry, whether we also have to impose that it's broken or gauged. When this parameter, when this current is gauged, it's equivalent to say that there is an action that is eating up the parameter. So it's like, yeah, like the typical things when you stabilize some scalars with the fluxes, then you get axial monodromy. This is the process of gauging these -1 for symmetries. If you want to say that it's broken, then exactly, it means that the parameter has to be dynamical. It means that you have to be able to deform the charge so that it's not conserved. And this process of deforming the charge, like for example, because you have domain words, or that you can deform continuously the parameter because it's a continuous parameter, is equivalent to breaking these -1 for symmetries. So the statement that there are no free parameters in quantum gravity is equivalent to say that there are no -1 for global symmetries.
I see. Okay.
It's something that it's something quite new. And also this year, I don't know, like we are trying to see if we can formulate this in a sharper way, because it's a bit exotic with the -1 for symmetries. But I really think that there is like a symmetry reason behind.
Okay.
Sorry,
Yes.
Rene. Sorry. In string theory, there are some special limits. For example, conical limit, large volume limit in the moduli space. If we try to localize in this point, one can learn something about this conjecture, for example, in this analysis.
Yeah, exactly. So I mean, the thing is that mostly all the models we do in string phenomenology, like when you trying to engineer the standard model or cosmology within string theory, they are always in one of these limits, because we want to have computational control. And these are precisely the limits in which we have computational control, when we go to large volume or weak coupling and so on. And it's precisely in these limits where string theory is telling us that there is also some new physics that is going to appear. So yeah, I mean, in those limits, the cutoff goes to 0, but we'll see that that's not only what happens. I mean, this tower of states can also have implications of what is the behavior of the gauge couplings or the scalar potential or the different quantities of your EFT as you approach the limit. And this is what gives rise then to the other conjectures of, okay, in general, the scalar potentials as you approach the limit has to have these features, or interactions have to have these features. And everything is a consequence of these towers becoming light. Okay. So it's like you have, like when you try to do string model building, it's like on one hand, you want to be close to these limits because it's when we know how to compute things. But on the other hand, we cannot be too close because otherwise the effective field is going to break down. And there is like some force pushing you in opposite directions. But yeah, we can learn for sure a lot about this string model building there.
Okay, thank you.
Okay, so these are the weak gravity and distance conjecture. So right now, I don't want you to pay special attention to the definition of the conjectures. I'm just going to focus on these, as I said, these universal features that both of them have, which is that we have these towers of states becoming massless as the gauge coupling goes to 0, or the field distance goes to infinity as we approach the boundaries of the moduli space. And the cutoff of the theory goes to 0 in terms of the mass of this tower. Okay. So first, what we are going to do is we're gonna see just some examples in string theory, like very easy examples of how this happens. Okay, now. And once we see these examples and we get an intuition of what these towers are and what's going on, we will define more properly what the conjectures are. Okay, that then claim that this feature, this pattern that we observe in string theory is more general and should be a quantum gravity phenomenon. Okay, so we'll give examples to understand the pattern from string theory, and then we'll formulate the conjectures and see how, especially for example, the weak gravity conjecture can also be derived from thinking about black hole physics. Okay. Okay, so I'm gonna take very easy examples first, like first in 10 dimensions. For people that know about string theory, maybe this is a bit boring. For people that don't know about it, I hope this can help to get some intuition of what's going on. So let me take type 2A string theory. So all you need to know is that the Lagrangian, the axiom that we have in 10-dimensional string theory has this form. So we have the Einstein gravity term. We have this scalar, which is the dilaton. Okay. So this is what parameterize the string coupling. And then we have never sparse, these are gauge fields. So we have on one hand a two-form gauge field, which is a never sparse field, and a one-form gauge field, which is a Ramon-Ramon. And we have other gauge fields, but I mean, there's no need to write everything. Okay, so we have different P-form Ramon-Ramon gauge fields. And it's important. We have always, when we check these conjectures, it's important that we have to be in the Einstein frame. Okay, everything is formulated in the Einstein frame. Okay, so let's imagine now we have only one scalar, which is this dilaton. Okay, so we can move in this field space. The distance when we move in the field space is the integral of the square root of the metric, right? So it's going to be logarithmic on this S, on this dilaton. Okay, and we can take two limits. One is the limit in which the string coupling goes to 0. It's like the dilaton goes to infinity. Okay. And then the tower of states that appears are just the string modes. Okay, so when the string coupling goes to 0, all the string excitations become light. So we have string modes with a mass given by the string scale, which is m Planck times gs to the 1/4, which in terms of the canonically normalized field, in terms of the proper field distance, indeed goes exponentially, right? When you plug this here, this is the exponential of delta phi. So this is the string perturbative limit. And also, since the gauge coupling of the two-fold gauge field goes as S, so yes, the square root of S inverse, the tension of the string is, since it's a BPS object, it's proportional to the charge. The tension is the string scale square. So indeed, the mass, okay, goes as the gauge coupling. Okay, the tension of this object goes as the gauge coupling, which is so the cutoff also goes proportional to the gauge coupling. Now we can take the other limit, which is that GS goes to infinity, or if we S goes to 0. And what happens here is that I have these 0 branes that become light, right? Because they are equal, the mass is the string scale over GS. So we get that this is the Planck mass, where GS to 3/4. And in terms of the canonically normalized distance, again, this is exponential. And the same, like, I mean, it's also proportional to the gauge coupling because the gauge coupling for the C1, which is the gauge field under which the D0 branes are charged, also goes to 0 in the limit, right? So the mass of the D0 branes, they are BPS, goes as the gauge coupling. And this is, what is this? Well, this is very well known. It's a decompactification limit in type 2A, because what we get now is an M-theory description in 11 dimensions. Okay, decompactification. Okay, so these are the two limits that appear in type 2A. And fun enough, even if we go now to more complicated compactifications, still everything that we find is always one of the two. Like either we find string perturbative limits or we find decompactification limits. Okay, is there any question?
Sorry, can you repeat this limit of the compactification, please? The idea behind this.
Yeah, so what happens in Day2A, yeah, is that you have this tower of D0 branes that are particles, okay, they are D0 branes that are becoming massless in terms of the Planck mass. And this tower of D0 branes, I mean, it's consistent with these conjectures, but the point is that when you take the limit, what happens is that they behave as a Kaluza-Klein tower. So the density is like a Kaluza-Klein tower. And what is going on, I mean, how string theory is resolving this infinite distance limit is that indeed one is growing an extra dimension because this is like the KK tower, so that is becoming light. And this is a well-known duality in string theory that what happens is that you get an M theory description. So when the string coupling goes to infinity, the type 2A string theory is not a good description anymore. Perturbative string theory is not a good description. You have an M theory description in 11 dimensions, in 1 dimension more, because you have opened up this extra dimension because of the KK tower. And that's the new description that appears that now describes the physics and so on. So type 2A at strong coupling is equivalent to M theory in 11 dimensions. Okay, and this is a well-known duality, but like you can also, I mean, it's the canonical example, no, of why we have these towers of states whenever we take one of the limits.
Yeah. Okay. Thank you.
Okay, so this is like a KK tower. Okay. So let me now also explain another example of this decompactification. So now we can take type 2A on a circle. Okay. So we get a new scalar, which is the radius of this circle. Okay. Which is this one, I call it phi here. Okay. And it parameterizes this would be the radius of the circle. Radius of the circle. And it also parameterizes the gauge kinetic function for the KK photon. Okay, the same than before that the dilaton was parameterizing the gauge couplings for the gauge fields. So here again, we can take two new limits regarding this new scalar, this radius. So we can take what would be the decompactification limit. So the radius goes to infinity. And indeed, what happens is that now we have a Kaluza-Klein tower that become light. So the KK modes go to 0 when they behave in general dimension as 1 over r squared, 1 over 2pr 2d minus 2. Okay, this is, you can find this formula in the literature. And if you write in terms of the canonically normalized field, in terms of the proper field distance, again, the KK modes indeed go exponentially. D minus 1, D minus 2, phi. Okay. And the same, the KK modes also are proportional to this gauge coupling. So you can plug, I mean, as you can see here, precisely the gauge coupling has the same exponential rate that we derive here. Okay, because I mean, this is like 1 over the gauge coupling square, right? So the KK modes, well, without the square, sorry, the KK modes go as the gauge coupling. We call it the gauge coupling of the KK photon. Okay. So again, we have a tower that goes proportional to its coupling and that decays exponential in terms of the field distance, and this is the compactification limit. Okay, but here we can take another limit, which is that the radius goes to 0. Okay, and what happens here? Well, I guess many people have already know this, but let me say it anyway. So what happens is that in string theory, we also have winding modes. So we can have strings that are wrapping this circle, and therefore when the circle goes to 0, they become tensionless. Okay, so we have new particles that are winding modes and that behave exactly the same as the KK modes when you replace the radius by alpha prime, so the string scale, over the radius. So this is what is behind this T-duality, okay, in which you can have a description. So we can either have type 2A on a circle, or we can have type 2B on a circle with inverse radius. Okay, and the tower of KK modes on one theory is equivalent to the tower of winding modes on the other one. So from the perspective, I mean, what is going on in this limit? Okay, we get all this tower of winding modes, but this is also a recompactification limit. Okay, because they are equivalent to a tower of Kekin modes in type 2b. So we are also growing an extra dimension. Okay. Any question? Okay, so all these towers of states, I mean, what I wanted to show you with this example is that they are very linked to the existence of dualities. Okay, so all the, I mean, if you study string theory, one of the first things you learn, because it's one of the revolutions in string theory, was the manifestation of all these dualities, the dualities, S-duality, the duality within theory, and so on. And precisely the way to, I mean, in which these dualities are manifest is because of the presence of these towers that imply a new weakly coupled description of the theory. So by understanding the nature of these towers, like understanding the nature of dualities in string theory. Okay, so let me summarize a bit what we have obtained. So there is always some tower of states that becomes light exponential in the field distance or proportional to the gauge coupling. So if we started in type 2a, right, we could take on one hand the limit in which the string coupling goes to 0, and that we recover the perturbative string theory. I mean, the quantum field theory breaks down. We need a full string theory to make sense of it. Or we can take the limit in which the string coupling goes to infinity, and then we recover an M theory description in one dimension more. Also, if we compactify in a circle, right, we can send this circle to infinity, and then we again recover type 2a, or we can send the circle to 0, and then we decompactify to 10 dimensions again, but in type 2b. Okay, so this is the duality. So the tower always implies a new weakly coupled description, coupled description of the theory. And in all the cases, the cutoff of the EFT goes to 0. So it's smaller than the Planck scale. Okay. So I like this because it's a very natural thing in string theory. Okay, like we're used to have these dualities all the time, like from many years ago. But still, from the effective field theory perspective, from someone working in phenomenology, it's actually very surprising that if you take one of these limits, like you send some gauge coupling going to 0, you are going to get a drastic new description of the theory. Like the cutoff is smaller, the quantum gravity cutoff, okay, so this is a quantum gravitational cutoff, is smaller than the Planck scale. So even if the Planck scale seems to be very high, and it seems that it's not going to give you any important implication for phenomenology because it's very high and gravity is very weakly coupled, that's not true in certain limits. It's not true in certain regimes because the cutoff is actually much lower than what you would expect. And this is something that we have learned from the very beginning in string theory, and I think we should take it seriously. Like it's a perfect example of something that is very natural in string theory, but very surprising from an EFT perspective. Okay, because now we are saying that effective field theories with tiny gauge couplings are problematic, okay, and effective field theories with large field ranges are problematic. So we have an upper bound on the gauge couplings and the field range that we can describe within effective field theory in terms of the quantum gravity cutoff. Okay, so tomorrow we will see, I will explain a little bit possible phenomenological implications because this can be used to constrain inflation and dark matter and other things, because there are many models in phenomenology in which we try to have very large field ranges or small gauge coupling. So you can use this to, I mean, this information from string theory to tell you what is the cutoff and what's going to happen. Okay. Any question?
Sorry, when you said large gauge coupling is problematic, do you mean just in terms of because it's non-perturbative, or did I miss something?
No, I mean small. Sorry, I mean so very tiny gauge coupling, very small one.
Yeah. Yes.
It's problematic.
No, I agree.
Yeah. Maybe I said it the other way around. I mean tiny in the sense of small.
Sure.
Okay, so what I'm gonna do now, so let's formulate these conjectures more precisely. What is the sharp statement, okay, behind? It's mainly based, okay, on these towers of states that are becoming light. And then I will give you some more complicated examples, okay, to see that this is not just about 10-dimensional string theory. Okay, so let me maybe start with the distance conjecture. So the distance conjecture is just formulated in words this phenomena that as we approach some boundary of the field space, we get some infinite tower of states that becomes light exponentially on the proper field distance. Okay, so the examples I gave you were very easy because we only had one scalar field. But in general, when we have a more complicated field space, this we have to study what are the geodesic distances. Okay, so this becomes exponential in terms of the geodesic distance as we move in this field space. And the exponential rate is supposed to be an order one factor. So in these examples that we checked, it's an order one factor, like 1 over square root of 2 or things like this. Is not specified by the conjecture. So this is one of the open questions. Okay, one of the main open questions of this conjecture is what is this exponential rate? Because in order to give precise phenomenological implications, we need to say exactly what the exponential rate is. And in recent years, we have made a lot of progress understanding what is this exponential rate. And there are lower bounds for it, depending on the level of supersymmetry and the dimension of the spacetime. Okay, that we will see. Okay, so this is the distance conjecture. So we have this tower of states, and therefore the cutoff of the theory breaks down exponentially. Okay. Then we have the weak gravity conjecture, which refers to the gauge theory when we have a gauge coupling. And so the formulation, what we call the electric formulation of the weak gravity conjecture, is that you must have some electrically charged state. So if you have a gauge theory with a charge to mass ratio that is bigger than the extremal charge to mass ratio of a black hole. Okay, so we'll see that this is motivated by black hole physics, but so it has the two motivations. One is the black hole physics, and the other is precisely these tower of states that are charged, because in all the examples that we see, when we take a weak coupling limit, okay, it's not only that we have one state, but we have this tower of sublattice of states, of super extremal states, that are precisely equal to the gauge coupling when they are supersymmetric. So in the examples I gave you before, they were like BPS states, and that's why the mass was like the gauge coupling. But in general, it could be that the mass is smaller than the gauge coupling, okay, smaller or equal than the charge, and the charge is proportional to the gauge coupling. Okay, so the idea is that in the weak gravity conjecture is a bit milder in the sense that just requires in principle some state that is super extremal. But in the weak coupling limits, when the gauge coupling is small, it becomes stronger and implies a tower or a sublattice of states becoming light. So the EFT indeed breaks down in terms of the gauge coupling. Okay. So the cutoff has to be smaller or equal than the gauge coupling. Okay. So I'm gonna show you some examples from string theory, like string theory motivation of this. And then once we finish with the string theory evidence, we'll discuss the black hole motivation.
Irene, can I ask?
Yes,
so this Q over M of an extremal black hole, right? You only trust this until the Planck mass. So do you have to make some kind of assumption of the corresponding state to an extremal black hole as you go below the Planck mass?
An assumption of whether the state is below the Planck mass, or
no? I mean, so suppose, I mean, you have this conjecture, you have this inequality in terms of the charge to mass ratio of an extremal black hole as derived by Einstein-Maxwell theory, but you only trust this when the mass of the object is bigger than the Planck mass.
You mean the black hole, like this extremal value?
Yes.
But
so
the idea is
I'm
that
just wondering,
Okay, finish. Yeah.
Well, I'm just wondering, maybe below the Planck scale, the corresponding state, which is an extremal black hole, maybe that corresponding state as you go below the Planck scale has quite a different charge to mass ratio. We don't know.
Yeah, okay. So when I say the extremal black hole, I mean, let me put it here. It's a black hole with a very large charge and very large mass. Okay, so this is a concrete order 1 factor that is fixed because it's the extremality, the charge to mass ratio of a very large black hole.
Yes.
So that approaches some particular value, and this is the value that enters in the conjecture. So what you require is that you have particles with a charge to mass ratio bigger than that value. Now, it's true that small black holes can receive corrections and can have a charge to mass ratio that is bigger or smaller than this value. And people are studying, maybe I will mention it tomorrow, but people have studied these corrections over small black holes with the hope or the goal of showing that the corrections, if you want to preserve unitarity, causality, and so on, are always such that the charge to mass ratio of small black holes becomes bigger than the one of a very large black hole. So that small black holes themselves are already satisfying the weak gravity conjecture. So it's a way to prove a very mild version of the weak gravity conjecture in which small black holes are the states that are satisfying the conjecture. It's a very mild version which wouldn't be used for phenomenology because it's just about small black holes. And the expectation is that maybe when the gauge couplings are strong and large and you are in the middle of the moduli space, maybe it's just about small black holes that are satisfying the weak gravity. But then when you take a weak coupling limit, you really have a tower of state that is becoming light. So they are not black holes. They are becoming massless. So it's, what we observe from string theory is that there is something stronger than just black holes satisfying the weak gravity conjecture that is realized.
But I guess what I mean is, would anything change if you had particularly surprising behavior of the charge to mass ratio below the Planck scale? Because so as you say, people compute these corrections for small black holes, but obviously they can't go below the Planck scale. Now, suppose the state below the Planck scale, has an almost vanishing mass and yet can carry a lot of charge, and that state can exist. We just can't we just can't calculate it. Does that change the story in any way?
It changes. The only thing that happens is that if you have a small black hole with a very large charge to mass ratio, then large black holes can decay to this small black hole. So if you just want to require, if the motivation for the weak gravity is just that black holes can decay, as we'll see, then small black holes are already enough to guarantee that large black holes can decay, but you still need to guarantee that these small black holes also can decay. So that's why in the end, you need to have also some particle where the small black holes can decay. So it doesn't really change much. It doesn't really matter. In the end, I think you're gonna need some state, could be very heavy, but some state to which all the black holes can decay.
Okay. Let me think and sharpen.
Okay, yeah. You can. Yeah. We can discuss it again when we discuss the black hole motivation. Maybe. Okay.
There's a question in the chat which appears.
Yes. Oh, I saw there was also another one that I didn't see before. I don't know. Well, maybe I can reply it anyway. So there was some question that I didn't see, which is what is the problem with tower of light states? The problem is that the Planck scale, since they are coupled to gravity, the Planck scale gets normalized. So the quantum gravity cutoff actually goes to zero, like gravity becomes strongly coupled. So you can, if you have infinitely many fields with coupled to Einstein gravity completely breaks down. Like this quantum gravity is like the Planck scale gets renormalized and the proper quantum gravity scale goes to zero completely. So the problem is just that the EFT weakly coupled to Einstein gravity breaks down. Quantum gravitational effects become important. Okay, and the question now is, weak gravity can be used for other concepts such as wormholes or white holes or black brain with this structure? Yes, so black brains, yeah, we'll see that this can be generalized and will be generalized to any black brain, like any p-form gauge coupling. So we require that we have p brain states that are electrically charged and whose charge is bigger than the tension of the object. Okay, so it works the same way, and we can compute it. And it even works for actions, and that's why people use it for implications for inflation. Like the action is like a zero form gauge field, and therefore you need to have instantons that are electrically charged and has an action that is smaller than the charge, which is 1 over the decay constant. Wormholes or white holes, wormholes are kind of related to these actions because you could say that the wormholes is like the equivalent of the black hole for the particle. So it's like the fact that wormholes can break because you have instantons is kind of the equivalent notion that black holes can decay into particles. And white holes, I've never seen anything like that. Okay. Okay, so in the remaining time, which is not much, I think I'm just gonna outline some of the other examples in string theory, okay? Because I don't want you to get the impression that this is just about like 10-dimensional string theory and perturbative and decompactification limits. Like why we are so confident about these conjectures is also because even when going to very complicated compactifications and very weird limits, still we can give general proofs that we get these towers of states. So I want to outline, briefly what these examples are, and tomorrow we will start, so today is about string theory, tomorrow we will start with the black hole motivation, and yeah, the black hole motivation, some of the refinements and the and phenomenological implications. And in the remaining time, we can discuss a little bit what are the other conjectures on the scalar potential and so on. Okay, so let me just give you some more examples. So first of all, you could say, okay, here you are just taking like radius and compactifications, very easy things. Let's take something more complicated. Let's take a Calabi-Yau threefold. And let's move in a direction that has nothing to do with the compactification or Kaluza-Klein towers and so on. So for example, in the moduli space of a Calabi-Yau threefold, you have, it's a product of the hypermultiples and vector multiples. So this is a 4D n equals 2 theory. And we can move in the complex structure moduli space of vector multiples. And what we can prove there in complete generality is that a tower of BP states become light at the infinite distance singularities of this moduli space. And this, what is nice also of these conjectures is that they are serving as a guide to uncover some new mathematical structures that are behind the compactifications and that are allowing these conjectures to hold in a very non-trivial way. So there is now a lot of connection with mathematics of the compactifications that is coming from studying these conjectures. So let me just outline how this is satisfied. So what happens is that at these infinite distance singularities, there is a monodromy transformation. Wait, I see there is a question. For the current values of the standard model theory we have, what is the estimate of the cutoff if we assume coupling to gravity? Yeah, so you can take the electron that is charged under the photon, and the gauge coupling of the photon, the point is that it's quite large in Planck units. So it's only 2 orders of magnitude, I think, or 3 orders of magnitude below the Planck scale. So actually the cutoff, according to the weak gravity conjecture, is very high. And that's because the electron is very super extreme, like the mass is much, much smaller than the gauge coupling in Planck units. So for this, the standard model satisfies the conjectures by a lot, let's say, okay? Now, when we try to add now beyond the standard model proposal, it becomes more interesting because typically we want very quickly couple things or light things for that matter, and then everything becomes much more constrained. Okay. Yeah, so let me outline this. So what happens at the singularities of the moduli space is that you have some monodromy transformation, which is so these scalars. So here we have some complex scalar. This is a complex manifold. So we have some, let me call it Si plus Ai. So we have some non-periodic scalar, some axion. So the shift symmetry of the actions are these monodromy transformations. Okay. And this monodromy transformation can be of infinite order or finite order. So infinite order means that there is no integer such that by going around the singularity, you come back to the same situation. Okay, so this is what means infinite order. And what we could show using some nilpotent orbit theorem of algebraic geometry is that the infinite distance singularities always are required to have an infinite order monodromy. Okay. And then by using these theorems, this monodromy can be used to populate an infinite tower of BP states. Okay, because the charges transform under this monodromy. So since it's of infinite order, we populate an infinite tower. And using, I mean, I don't have time to explain, but using these theorems, you can show that in general, for any Calabi-Yau, the tower of BP states will behave exponentially in the field distance, where this alpha is bounded by these monodromies, by some properties of these monodromies, transformations. Okay, so that in a Calabi-Yau threefold, it's always bigger than 1 over the square root of 6. Okay, so this is just an example of a more complicated manifold in which one can show in general that you always have these towers of states. And the last one, and I finish, let me just say it very quickly, you could also consider, like, we say, okay, but this is just about closed strings. What about open string gauge fields? Like, can I somehow engineer a situation? So here with the gravity, right, we want that the mass is smaller or equal than the gauge coupling in Planck units. Can we engineer a situation with open strings such that the gauge coupling is fixed, but the mass becomes very large so that I will violate this conjecture, no? So that they never become massless? And you could think of naive situations in which you could try to do it. Like you have, for example, DC branes in some compact manifold, and the gauge coupling of these DC branes is given by the square root of GS. So if you keep GS fixed, the gauge coupling will be fixed. But the mass, we have open strings in between, and the mass is given by the distance between the branes. So you could say, okay, so let's move the branes very far away so that the mass becomes very large and will violate this. I don't have towers of states becoming light, and they are not proportional, or they are bigger than the gauge coupling. The problem is that if you try to make this very big, very large, since the space is compact, because we want to keep the Planck mass finite, at some point, I mean, you cannot make this as large as you want. And precisely, you can see that the mass, when you try to make the mass very large, like by making this distance large, the Planck mass also goes to infinity in such a way that m squared over the gauge coupling over the Planck mass, so in Planck units, this is always smaller than 1. Okay, so there is no way to engineer this in a compact space. And also even considering, so there is a lot of work, we put the reference of Lee, Lerche, and Weigand, in which they try to engineer situations in which you keep the overall volume fixed because you make some cycle very large and another cycle very small, and try to engineer situations that would violate these conjectures. But then when you do that, there is still, so when you try to make some cycle very large, so the gauge coupling goes to 0, but then there is another, and the Planck mass remains fixed. Okay, this is another option. Then there is another circle that goes to 0 to make this possible. And then there are towers of states associated to this other cycle. So again, the weak gravity conjecture and the distance conjecture is always satisfied. So you can find these examples in more detail in my lectures if you are curious about it. But the upshot is that somehow string theories are always finding a way to satisfy this. And the next goal is try to understand why this is a general feature of quantum gravity. I mean, why it should happen, okay? This is just like string theory examples, but why this should happen in complete generality, and this is what we will try to discuss tomorrow, also thinking of black hole physics. Okay, sorry that I ran out a bit of time, and let's stop here and see if there are more questions.
Let us thank Irene for the lecture. And
as always, to stop and interrupt me and ask questions, feel free to enter a question in the chat window, or just pipe up, unmute yourself, and let me know if anything I say is unclear, or if you have any comments or questions, anything like that. So in my lecture today and tomorrow, what I really want to do is flesh out the two main examples of averaged holographic dualities. And we've spent, a lecture and a half or so kind of, motivating this, setting up some groundwork. And what I'd really like to do today is just dive into the detail. So the first model that I want to discuss is JT gravity, which is a two-dimensional theory of gravity. And the action for this theory is quite simple. So it involves a metric and a standard Einstein-Hilbert term in 2 dimensions. The coefficient of the Einstein-Hilbert term is Newton's constant, but it's called S0 for historical reasons. Generally speaking, it's because JT gravity arises as a dimensional reduction from some higher dimensional theory down to ADS2. And if you have some, for example, ADS2 cross S2 near horizon geometry of some black hole, that coefficient S0 would represent the entropy of that black hole, or be related to the entropy of that black hole. There's a second very important term in the action involving a scalar field phi. And then there are various boundary terms that are important, but about which I won't say too much, since at this point I'm trying to just give you a slightly more general overview. But the basic idea is that the equation of motion for phi essentially acts like a Lagrange multiplier to set the curvature of our 2-dimensional surface to be negative and constant. So what that means is that this is a theory of constant negative curvature surfaces. So, for example, if we wanted to compute some partition function of the theory, so here we're talking about a theory that's defined in Euclidean signature. And you could imagine computing, for example, the partition function of the theory where our boundary is a circle with some length that I have called beta, because of course, the circle will be interpreted as a Euclidean time circle, and the length would be interpreted as the corresponding inverse temperature. Then the way that we would compute this is by summing overall constant negative curvature surfaces whose boundary is a circle of length beta. So for example, one contribution would be a disk. The next contribution would be a disk with a handle glued in, and so on and so forth. And the point is that the higher genus terms in this expansion are suppressed by factors of that Einstein action, e to the s naught root g r, appearing in the JT action gravity. And because we're studying a constant negative curvature geometry, root gr is just given by the Gauss-Bonnet theorem. So it's just the Euler character of the two manifold. And so these will be suppressed by factors of e to the minus s naught times the Euler character. So when we compute a gravitational path integral and think about a genus expansion, then the higher terms in the genus expansion are going to be suppressed by these factors of e to the s naught times the Euler character. So for example, the disk has Euler character -1. So this would go like e to the s naught. Every time you glue in a handle, every time you increase the genus, the Euler character drops by 2. So you'll get an e to the, an e to the minus s naught for this term here, and so on and so forth. Okay. Similarly, if you were to compute more complicated observables, say, for example, if you were to compute the path integral with a pair of circle boundaries, then the leading term would involve a cylinder, and then you would have subleading terms. So for example, a cylinder with a handle glued in. And again, these would be suppressed by factors of e to the minus s times the Euler character. So this would go like this first term would be order 1 because the Euler character is 0. This term would be down by a factor of e to the minus 2 s naught, and so on and so forth. And the basic idea of the correspondence between JT gravity and some sort of matrix integral is the usual idea that we always have in the back of our head when we're thinking about holography, which is that we think of the genus expansion as the large N expansion in a gauge theory. But of course, here we're talking about a two-dimensional theory of gravity. So that should correspond to some kind of one-dimensional gauge theory. That is to say, just as some kind of matrix integral or some kind of matrix model.
Can I ask a question?
Please.
I'm just a bit confused by the definition of JT gravity. So
okay.
You said that it's a theory of constant negative curvature surfaces, right?
Yes.
But so if you have a constant negative curvature on a surface, you need the genus to be greater than 0, right?
So if you have no boundary, but remember here, for example, the disk has a boundary, and so you'll get an e to the s naught because the genus is -1.
Yeah, I mean.
So for example, last time we wrote down the hyperbolic metric on the disk, and that would be an example of a contribution to this path integral. You know, there's some bells and whistles that I'm suppressing here. So for example, the boundary terms are very important. And in fact, a lot of the non-trivial work that goes in here involves carefully keeping track of these boundary terms. So for example, you might think that, you know, the constant negative curvature metric on the disk, how complicated could that be? But there actually is a little bit of work that one has to do in calculating this disk amplitude. And all of that work comes into the fact that you have to pull this boundary into finite distance and imagine all possible boundaries of specified length that are embedded in this disk and then integrate over these possible, boundary wiggles, these possible embeddings of the boundary in the disk. And that's where the sort of non-trivial calculation of, for example, the disk amplitude or the cylinder amplitude comes in this JT gravity theory. It's not a terribly difficult calculation. So for example, it was considered by Stanford and Witten, where it was shown to be one loop exact. One can compute it exactly, but nevertheless, there's a little bit of a calculation there. For the sake of time and to keep things, relatively simple, I'm not going to focus too much on the details of that boundary calculation.
Okay.
But the main punchline is that this theory of gravity is a 2D theory of gravity. It has a simple genus expansion. And we're going to try and interpret that genus expansion in terms of some kind of matrix integral. In the usual way that in higher dimensions, you might interpret a genus expansion in terms of some large N expansion in a gauge theory. Good.
Sorry, Alex, I have a small confusion.
Mm-hmm.
So when you say that the boundary theory is a matrix model, so wouldn't that be a zero-dimensional gauge theory?
Let me tell you exactly what I mean. Let me write it down, and then you can you can tell me exactly what your question is. But it's really a matrix integral. That's perhaps what I should say better.
Sorry, Alex, could I just quickly ask a question to clarify something, a bit following up on the previous question? So here you're in 2 dimensions, and also you're in Euclidean signature.
Mm-hmm.
And so you're considering this path integral over metrics, which match onto some boundary. But is it because you're in 2 dimensions that you don't have to worry about? So first of all, like you were saying in the previous lecture, are you integrating over real metrics here? And is it because you're in 2 dimensions that you don't have any problems with negative modes? And
I'm integrating over real metrics. Let me talk in a little bit more detail about how exactly I'm going to think about that. Let me proceed, and I'll say a few more words about how we think about that integral over metrics. So strictly speaking, you would have to worry about some very complicated gauge fixing procedure. And if you look, for example, in the paper of Saad, Schenker, and Stanford, that's gone through in some amount of detail. But actually, I think there's a very simple, intuitive way of thinking about that integral over the space of metrics, which we'll get to in just a second. So maybe I'll proceed, and you guys can then repeat your questions in a few minutes if something is still unclear. Okay. But really, the question is what kind of matrix integral should we be talking about here? And the idea is that because we're studying a one-dimensional CFT, that is to say, a one-dimensional quantum mechanical system, I want to think about this as an integral over possible one-dimensional Hamiltonians. And a Hamiltonian of some quantum system is just some n by n Hermitian matrix. And the genus expansion is supposed to be the 1 over n expansion of some Hermitian integral over Hermitian matrices. These Hermitian matrices being interpreted as the Hamiltonians of some one-dimensional, of some quantum system. So in particular, the statement of the duality, statement that I'm not going to prove to you, but I will sort of indicate to you how we should think about its proof, is that the observable that we would compute is the JT gravity path integral. So this would be, loosely speaking, an integral over this space of constant negative curvature metrics, weighted by an appropriate Euclidean action. And you want to imagine that we're integrating over manifolds M, 2-dimensional manifolds, whose boundary is the disjoint union of a bunch of circles of lengths beta 1 all the way up to beta n. So they're going to be an integral over a space of manifolds where you have n boundary circles. And then this turns out to be equal. Well, I should really put a squiggly line here. Equal in a certain sense to a matrix integral. So here, this is going to be an integral over n by n Hermitian matrices. Times some measure that is interpreted as a probability density on the space of matrices. And then this is going to be a function of those lengths that I call beta. And in particular, it's going to be the integral with this probability measure of n finite temperature partition functions of this matrix integral, okay? So when we say that we have an averaged holographic duality, this is exactly what we mean. That there is an equality up to that little squiggly sign that I'll explain in a second between a gravitational path integral and an average over Hamiltonians of quantum mechanical systems for some Hilbert space of size m. And the length of the boundary circle is literally interpreted as the temperature of this quantum mechanical system. So here we are literally computing the expectation value of some endpoint function of the partition function of a quantum mechanical theory, okay? And here, this angular bracket denotes the expectation value with a particular probability measure. Okay? So this is the statement of the JT gravity matrix integral duality. A few comments are in order. The first is I should tell you exactly what I mean by this squiggly sign. So the squiggly equals means that these two expressions on the left and the right-hand side of this integral agree at all orders in 1 over n, which I remind you was e to the s naught on the gravitational side, where s naught was basically 1 over Newton's constant, okay? So this is an agreement at all orders in perturbation theory in the matrix model, but an agreement that is true at all orders non-perturbatively, that is to say what we would call in an instanton expansion on the gravitational side. Okay. They do not agree at finite n, in part because I don't even know how to define the left-hand side of this expression at finite n. And so if anything, we might use a matrix integral of this sort as a definition of JT gravity at finite n. And that would involve including what we would think of as doubly non-perturbative effects, effects that are non-perturbative on the matrix model side, okay, so they would go like e to the minus n, but would be doubly non-perturbative. They would go like e to the 1 over Newton's constant on the gravitational side. Okay. And I don't want to go into too much detail about how this is derived, but let me tell you a little about why this works. Okay. So why does this work?
Quick yes. Question. You said S0 is can be associated to some entropy. Is that why its exponential is always 1 over an integer? So how why is e to the S0 always 1 over an integer?
This isn't really. I mean, this is no. I mean, we're working in a large n expansion where the fact that n is an integer is really invisible. So I think it would be a little unfair to think of our gravitational theory, at least as defined in the way that we have done it here, as knowing anything about the integrality of it. Yeah, I think that would probably be stretching it a little too far.
But so should that be to the minus S0?
Yes, I'm sorry. I was a little sloppy about that.
Thanks.
Good, thank you. Any other questions? Well, I think as a way of kind of addressing some of the questions that came up a few minutes ago, I just want to indicate very briefly about why this works. Okay, so why does this work? Well, what is an integral over a space of constant negative curvature metrics? Okay. So let's imagine that we're trying to do this integral over metrics on a manifold of some specified topology. Okay. So it turns out, and this is a famous fact in mathematics, that if you have some constant negative curvature surface, so it could either be sorry, my window keeps resizing there. It could either be a compact surface or a non-compact surface. So let's imagine that we have some non-compact surface. So here I've drawn a contribution to what I would call Z of S1. So it turns out that there is a finite dimensional space of negative curvature metrics on this manifold. And the integral over the space of such metrics is going to be the volume of the moduli space of these constant negative curvature metrics on this manifold. So in particular, one way of characterizing the moduli space of constant negative curvature metrics is, and here maybe I'll make my life a little more interesting to draw a more complicated case. So let's draw something with two handles. So the basic geometric fact is that you can always think of a constant negative curvature manifold as being a sum of a bunch of pairs of pants, okay? And so here, what we imagine doing is representing this surface as a bunch of pairs of pants glued together. And there is a unique constant negative curvature metric on a pair of pants, provided you specify the lengths of the geodesics at the cuffs of this pair of pants. And so because of that, there is a finite dimensional space of such metrics, and a coordinate system on the space of such metrics would be given by a length parameter for each one of these cuffs. So here, for example, I've drawn 1, 2, 3, 4, 5 different cuffs. Those are those little circles. And the coordinates on the moduli space of surfaces would be a length parameter for each cuff, along with an angular parameter, because whenever you have two cuffs, you can glue them together with some kind of relative twist. So here, the relevant moduli space would be 5 complex dimensional, or a 10-dimensional space. And so there would be some complicated 10-dimensional integral that you would need to do in order to compute this moduli space volume. Okay. Now, in principle, such moduli space volumes are quite complicated to compute. And indeed, there are no known closed form expressions for these volumes of moduli spaces. But it turns out that although they have not been computed exactly, these moduli spaces obey various recursion relations. And in fact, there are various different recursion relations that have been discussed in the literature, many of which were motivated by some of the relationships between these and matrix integrals. But for our purposes, the relevant recursion relations were written down by Mirzakhani about 15 years ago. And it turns out that these recursion relations turn out to be equal to the equations that are obeyed by the partition functions of matrix integrals. And so depending on whether you're a mathematician or a physicist, you have different names for the recursion relations obeyed by matrix integrals. If you're a mathematician, you call these loop integrals, loop equations. If you're a physicist, you call them Schwinger-Dyson equations. Or if you're a normal person who's neither a physicist nor a mathematician, you call them integration by parts identities. Of some rather complicated matrix integral. And the basic observation then is that because these moduli space volumes that appear in the computation of these gravity path integrals obey the same recursion relations as those in a matrix integral, and one can also check that the starting point of this recursion relation, which happens to be this disk amplitude and cylinder amplitude that I wrote down above, obey the same starting point as the elements of these recursion relations. That is what allows us to sort of prove this duality between great JT gravity and a matrix integral. One comment that I should make is that I have not written down the probability density over the space of Hermitian matrices. And the reason I haven't written down is that there's no simple closed form analytic expression for it. So P of H, this probability density, is rather complicated to write down. And it is usually discussed as being defined only implicitly through what is known as the spectral curve of this matrix integral. So one could study it perturbatively. We could plot it for you in certain approximations, but it's not something that is sufficiently easy to write down. It is not, for example, just a Gaussian distribution over the space of Hermitian matrices, but rather it's something rather more complicated. Okay. So hopefully, I'm not sure if this at least, I think, schematically answers some of the questions that were asked earlier. There are a lot of details that go into this calculation that I'm glossing over here. So for example, one thing that is not at all clear, I think from what I have said so far, is what the induced metric on the moduli space of constant negative curvature surfaces is with respect to which one has to compute this volume. Okay. So for example, when mathematicians talk about volumes of moduli spaces, they usually have a particular volume element or symplectic structure on moduli space that they're thinking of. That's the Weil-Petersen moduli volume element. One calculation that one has to go through and check is that when we talk about the integral over constant negative curvature metrics on this space, that the induced volume element on this space of metrics is the same one that the mathematicians know and love. And that's something that one can check, but it's a little bit non-trivial, because when we think about doing an integral over a space of metrics, we're really thinking about some infinite dimensional integral. When we talk about the moduli space of constant negative curvature metrics that has been turned into a finite dimensional integral. And so you need to be rather careful when you figure out, for example, the Fourier-Popov determinant or the Jacobian factors that arise when you zoom down to this finite dimensional integral. Fortunately, it all sort of works exactly as you would expect. One way of proving this is to rewrite JT gravity, not as I have done above, where I wrote it in terms of a metric and a scalar field, the dilaton. Instead, it turns out one can alternatively formulate it in a language that's a bit closer to a gauge theory. So it's a BF theory for SL2R. And then one definition of this Weil-Petersen symplectic structure is that it's the natural thing that you get from BF theory or from Chern-Simons theory if you're working in one higher dimension. So I don't think it's necessarily super instructive to go through that in detail, but I thought I would just mention it. Okay. So this, I think, is...
I have a question. I think I didn't really follow, but so you say this holds, this Z can compute on both sides if you go up a little bit to all orders in N. But then at the same time, you also said that this probability distribution you only know in certain regimes because it's very difficult to write down.
Well, we know that the probability distribution is typically, there is an exact probability distribution, but it is not written down. It's typically not presented as a function of the Hamiltonian, but rather it is defined implicitly through a different object that is known as the spectral curve, okay? Which is a gadget. Yeah, it's a gadget that you can use to compute these matrix integrals, recursively in a 1/n expansion. Okay. So, I don't want to. If you don't know what a spectral curve is, don't worry, because it's not like, it's just some technical tool that we use when we calculate large N matrix expansions of this type. Good. But basically, it's a different way of encoding this probability distribution that is particularly well adapted to the 1/n expansion. I think that's probably the best way of thinking about it. Okay. Essentially, the spectral curve encodes the same data as that disk amplitude. Okay. Great. And are there any other questions?
Yes, Alex, can I make you a question?
Please.
Do you hear me correctly?
Yes. Please,
okay.
Please.
Okay. So maybe this is related with the topic you wanted to discuss in the previous lecture, but from the gravity point of view, this object that you have defined on the left-hand side, this set JT of several temperatures, is it something that, from the gravitational point of view, is it natural to propose? And a connected question related to that is the following. You mentioned also in the previous lectures that when you have these canonical examples of ADS 5 crosses 5, and you have sort of like a P of H, like the distribution becomes like a delta or something that is picked in a strict theory. But can I now grab, for example, several copies of this N = 4 super young Mills? Let's say in spheres, I put several spheres, and then I induce this ensemble. I put several copies, try to do like a gravitational computation, and these copies become entangled or connected or something.
So first of all, I think we should be careful about the word entangled here. Entangled is a word that we talk about in Lorentzian signature when you're talking about states in the Hilbert space. So if you have a Lorentzian wormhole, that is to say a black hole, then in the standard ADS CFT picture of an eternal black hole, that is represented as an entangled state between two states in the Hilbert space. Here, what we're talking about is something very different, where we have Euclidean wormholes, which lead to a probability density on the space of theories, not an entangled state in a Hilbert space. So just to make sure that we're all on the same page. This is not entanglement. This is a probability distribution on the space of theories. Here, the probability distribution is that function I called P of H. And so the space of theories is literally the space of quantum mechanical Hamiltonians represented as n by n Hermitian matrices. I mean, what could be simpler, right? That's a space of Hamiltonians that we're literally integrating over. And then if I hand you a Hamiltonian, what is the observable? What is the only thing that you could compute? Well, a Hermitian matrix is up to unitary equivalence, completely characterized by its spectrum. So the only thing that you could compute, the observables that extract all of the data about this probability distribution, all of the unitarily invariant data of this probability distribution, are just trace of e to the minus beta h, along with its various correlation functions, right? The things that I've called, expectation value of z of beta 1 up to z of beta n, right? Where literally z of beta is literally trace of e to the minus beta h for this probability distribution. Okay. And then your question was really, is this the natural thing to compute on the gravity side? And I would say that if you think about, how we defined a theory of gravity in ADS, is that it is a theory where we integrate overall metrics in the interior with some specified boundary conditions out at infinity. And so the only thing that you can compute in a gravitational theory is a partition function that is a function of those boundary conditions out at infinity. And if you're thinking about two-dimensional metrics with one-dimensional boundaries, the only boundaries that you can have are circles. And the only data that you could ask about is the length of that circle. So this z of beta 1 up to beta n from a gravitational point of view is kind of the only observable, or it is the sort of maximal observable that you could imagine asking for in a theory of gravity that includes only a metric field. Of course, if our theory of gravity had more interesting degrees of freedom in the bulk, let's say that you were integrating over other local fields as well, you could introduce sources for those fields on the boundary. Then you would have more interesting kinds of observables to compute. But this is a very simple theory of gravity where the object that I have written here is the only thing to compute. And it's the only thing to compute on the gravity side, and it's the only thing to compute on the matrix integral side. Now, part of your question was a question about, what happened, how should we think about this in comparison to theories where we only have a single Hamiltonian? And I think that's a very interesting question. So one question that you could ask is, what would happen if we tried to change this probability distribution so that instead of having some, probability distribution supported everywhere, all over the space of Hermitian matrices, we had just a delta function supported at a single Hermitian matrix? That's a complicated question. Some things can be said about it, but roughly speaking, the idea is that as you go away from this probability distribution, the gravity theory starts looking less and less like a simple gravity theory whose path integral we can compute exactly, as we have done in this example. And it starts looking like something more mysterious from the bulk point of view. And we'll see this again. And so, for example, you asked about type 2 string theory. So, for example, you could ask about, what is the partition function of type 2b string theory where I have multiple boundaries in Euclidean signature? And the answer is that if type 2b string theory on ADS5 is dual to exactly n equals 4 Yang-Mills, then it must factorize exactly. The issue, however, is that I don't think that we have an independent bulk calculation of that in type 2 string theory. We certainly don't know of any Euclidean saddle points that connect two boundaries that are disconnected, say, S4s or something like that in Euclidean signature. So there is certainly no saddle point contribution. But that is not to say there couldn't be other non-saddle point contributions to the path integral. And that's actually a very important lesson of this JT gravity theory, because one of the things that is important to note, I didn't dwell on it here, is that this is a full integral over spaces of metrics, not just those that are solutions to the equations of motion. Okay, I didn't really write down the theory in full gory detail, but it turns out that the geometries that I'm integrating over here are not just solutions to the equations of motion, but they are an integral over the full space of metrics.
Okay, amazing answer. Thank you very much.
Thank you. Thank you. It's an amazing question. Good. Okay, great.
Alex,
So this,
I have a
please.
question.
Great.
So since on the JT side, things are defined only in the 1/n expansion, because there is just one level of the non-perturbative effects. So does that mean that the probability distribution that would make this identity work is really only defined in the 1/n expansion, right? It's not defined at finite.
I think that's exactly right. I think that's exactly right. I think that's exactly the correct point of view. The spectral curve defines this probability density in a 1/n expansion. And so if you really wanted to define this at finite values of n, you would have to define a probability distribution as a function of n that goes over to this thing at infinite n. And my understanding is that there is not a unique choice for such a thing. And so that there could be many potential UV completions of JT gravity in that sense.
Yeah. And sorry, another quick question. Sorry.
Oh yeah, maybe I'll answer one more sentence, which is that in the next example that I'll consider, there is at least a plausible, more or less unique choice of probability distribution at finite n. Okay, we can argue about how unique it is, but there's a natural guess. Yes. But you were saying.
Yeah, the other question is, so in ADS-CFT, usually on the filter side, we have a CFT. So here, is there some constraint on this probability distribution in order to have a CFT in some sense?
Really, I mean, this is really, so one famous fact about, okay, great. So are these individual Hamiltonians appearing here, Hamiltonians of conformal field theories? And the answer is that they can't be, because what is a conformal quantum mechanical system? So a conformal quantum mechanics system is one that has a Hamiltonian that sits inside SL2R. And a straight exercise, okay, a great exercise for anyone who hasn't done it, is to show that any such Hamiltonian has a continuous spectrum. Okay. So it's impossible to have a Hamiltonian that sits inside an SL2R that has a discrete spectrum. So what that means is that you shouldn't think about these Hamiltonians actually as individual CFTs. So for that reason, this JT gravity matrix integral duality fits in not in standard ADS-CFT, but what people sometimes call nearly ADS2, nearly CFT correspondence. Yeah, great question.
Okay, thanks.
It's related to the fact that, the precursor to all of this JT gravity stuff was the SYK story, where it was noticed that a particular disordered quantum mechanical system in one dimension, the SYK model, which is a theory of four fermion interactions with some disordered coupling constants pulled from an ensemble. This is not a conformally invariant theory, but it is a conformally invariant theory in the infrared. And so it looks like something that could be dual to an ADS theory of gravity at low energies, but not exactly. Okay, great. And in fact, it's because of these issues, I mean, this is maybe a good place to move on, that we tried to consider other examples, which are maybe a little closer to the spirit of the ADS-CFT correspondence. So the second example that I'd like to talk about maybe for the rest of the time today is a different example. Where we average over a space of CFTs. And in particular, if you wanted to try and construct a version of this averaged ADS-CFT duality, where your theory of gravity is a little bit richer than just gravity in 2 dimensions, you might want to try and average over 2-dimensional CFTs so that you have a 3-dimensional theory of gravity. And there are various reasons why this might be interesting. So one reason is that theories of gravity in 2-dimensional ADS are extraordinarily simple. And there's a sense in which they don't contain black holes. I mean, there are ways of thinking about ADS2 itself as a black hole, say in Rindler coordinates. But in three-dimensional ADS gravity, there are genuine black hole solutions. There is an ADS Schwarzschild black hole whose entropy you could hope to count, and whose degrees of freedom you could hope to explain. And so a richer example might be an example in higher dimensions. And two-dimensional CFTs and three-dimensional theories of gravity seem like a great place to try this. One reason being that two-dimensional CFTs have an infinite symmetry algebra, the algebra of Virasoro symmetries. And so they're much easier to study than CFTs in even higher numbers of dimensions. Okay. So a different and sort of more ambitious goal might be to try and formulate a version of this averaged ADS CFT duality, where we integrate over a space of two-dimensional CFTs. So to begin, let's ask how we would do this. So what would we need? In order to average over a space of two-dimensional CFTs. Okay. So to begin, let's try and remember what is the data that defines a 2D CFT. So a CFT is defined by a list of operators, and in particular, a list of primary operators, along with some data. So in particular, you need to specify the spectrum of the theory. So their dimensions and spins, along with a set of coupling constants. And the way that we characterize coupling constants in conformal field theories is in terms of operator product expansion coefficients, or three-point coefficients. So here we would call these CIJK, and roughly speaking, they're the three-point functions. They're of these operators, which tell you how, if you take O1 and O2 and expand it in a basis of operators O3, what those expansion coefficients are. And so this set of data is the set of data that defines a two-dimensional conformal field theory, or indeed a conformal field theory in higher dimensions, although the spins would not be numbers there, but instead representations. In any case, if we wanted to define an averaged theory of gravity by averaging over a space of CFTs, then we would really need three things. The first thing that you would need to do is determine the possible values of this data, delta I, Ji, and Cij. Then you would need to find some probability distribution on this space of data. And finally, you need to compute averages and compare to some theory of gravity. Okay, so these would be the three steps in order to define an ensemble of CFTs. And this really generalizes the notion of a matrix ensemble. Now, if you have a matrix like the Hermitian matrices we were discussing in JT gravity, a Hermitian matrix is determined entirely by its spectrum, okay? And so we don't have to worry about these three-point function coefficients. Essentially, when you integrate over, when you define a Hamiltonian, you're specifying some set of eigenvalues. And then you would just need to define some probability distribution on the space of eigenvalues. Okay. So for a Hermitian matrix, a matrix integral, step one is done. It's just the set of eigenvalues. But for conformal field theories, of course, even step one in this process is very, very complicated. And in particular, step one has a name. It's the conformal bootstrap problem. Okay. So even step one in this procedure is a very difficult thing to carry out. You would be rich and famous to the extent that physicists get rich and famous if you could solve step one of this procedure. So even at the beginning, it seems like this is a very difficult thing to try and carry out. And so in order to make our lives easier and to have a hope of solving this, what I'm going to do is what we always do as physicists when we're confronted with a problem that we can't solve. What I'm going to do is I'm going to add symmetry to the problem until we can solve it. And in particular, what I would like to do is add as much symmetry as I can to the problem while still keeping this problem non-trivial. Okay. And it turns out that when we do so, we're going to be able to carry out all three of these steps explicitly. So we'll be able to solve the bootstrap problem. Well, we won't solve the bootstrap problem. We'll cite people who solved it many years ago. We'll define a probability distribution on the space of conformal field theories. And then it turns out that we'll be able to compute averages. And just as in the matrix integrals described above, the most general average that you could compute was an average of trace of e to the minus beta h to some power. We'll be able to compute the average of an arbitrary observable in this theory. And we'll see that it does have a simple interpretation in terms of ADS gravity. Okay. So in particular, what we will do is we're going to consider CFTs with some central charge that I'll take to be an integer that I'll call D, and with as much symmetry as possible consistent with that central charge. Now, in a two-dimensional theory, the way that we characterize symmetries is in terms of a chiral algebra. The reason being that the conservation law for a current in two dimensions, d mu, j mu is equal to 0, is just another, you can always write that in complex coordinates as d bar j sub z is equal to 0. So that means j sub z is holomorphic and j bar is anti-holomorphic. So we characterize symmetry algebras in two dimensions in terms of an algebra of chiral operators and anti-chiral operators. So in particular, the biggest algebra that I could consider that is consistent with this central charge is just to have a bunch of U1 currents. So a bunch of dimension 1 chiral operators. And it turns out so that there is a finite dimensional space of such theories. So it's dimension d squared with a, let us say, canonical or natural probability distribution. And finally, that it turns out that there is a beautiful mathematical tool that one can use to compute integrals over the space of theories with this probability distribution. Okay. And again, this is not something that we physicists invented. This was known to mathematicians some time ago, where it was quite popular in number theory, and it goes under the name of the Siegel-Bay formula. Okay. So maybe, though, rather than trying to dive into any technical details right now, I should pause and see if there are any questions. And in fact, I believe if this was a 50-minute lecture, I should probably just stop here. But of course, I'm very happy to answer questions or ask questions to anyone who has any. Thank you.
So let's thank Alex for the lecture.
Thank you.
And yeah, now we can stop recording and go to the discussion session.
Oliver?
Sorry, we just wait a little bit.
Okay, should we wait? Okay.
Till this till the recording.